Today I am going to discuss about the topic torque on a bar magnet in a uniform magnetic field. When a bar magnet placed in a uniform magnetic field at an angle theta, then what will be the torque experienced by this bar magnet here? According to the modern view, each atom of this bar magnet is behaves like a small current loop. क्यों? Because a current loop is behaves like a magnet. So we can assume each atom of this bar magnet is behaves like a current loop क्योंकि इसका हर एक एटम एक मैग्नेट की तरह बिहेव करेगा. तो अगर ये एक मैग्नेट की तरह बिहेव करेगा तो हम एज्यूम कर सकते हैं कि एक क्या है ये, इट कैन बी एज्यूम्ड एज ए टाइनी करंट लूप which are oriented in same direction. So we can assume each atom of this magnet we consider as a current loop according to the modern view. And we know that if a current carrying loop placed in a uniform magnetic field B at an angle theta, then it experiences a torque. And the magnitude of that torque is given by tau is equal to I A B sine theta, where I is what here? We can assume I is the current in that small current loop. A is the area of that current loop. B magnetic field, and theta is what here? Angle. And now the total torque acting on each loop be taken as the total torque act on this magnet placed in this uniform magnetic field at an angle theta. इसका मतलब हर लूप जो हम एज्यूम किए हैं, हर लूप के हम निकाल दें मैग्नेटिक टॉर्क जो कितना है, और सबका सम जब कर देंगे तो द सम ऑफ द टॉर्क विल गिव द टोटल मैग्नेटिक टॉर्क एक्टिंग ऑन द बार मैग्नेट इन यूनिफॉर्म मैग्नेटिक फील्ड. सपोज ऑन ईच लूप torque is I A B sin theta, and in this way, in this bar magnet, if we consider there are n current loops. So for n current loops total torque, for n loops, you can see it tau is equal to n I A B sin theta, and this torque acting on total current loop we consider as a torque acting on the bar magnet placed in this uniform magnetic field B at an angle theta, where theta is what here? Angle between the axis of this bar magnet with the magnetic field. And in this way you can say here tau is equal to NIAB sin theta. At place of NIA we can write magnetic moment. So we can write here tau is equal to MB sin theta, where m is equal to how much? NIA. This m is called magnetic dipole moment. M is equal to NIA. So at place of NIA we can write MB sin theta. And in vector form we can write here tau is equal to vector m cross vector b, because A cross B, AB sin theta is m cross B, MB sin theta. And the direction of this torque acting on this one is perpendicular to the plane of magnetic moment as well as the magnetic field. Second thing here, we can consider, already I have discussed in chapter electrostatics, the torque experienced by an electric dipole in uniform electric field. याद करिए कि कोई इलेक्ट्रिक डाइपोल जब किसी यूनिफॉर्म इलेक्ट्रिक फील्ड में रखा जाता था तो उसके ऊपर भी एक टॉर्क लगता था, एंड दैट टॉर्क वाज गिवन बाय टाउ इज इक्वल टू PE sin theta, where P is called electric dipole moment, E electric field, and theta with the angle between the axis of this dipole from the electric field. तो इस इक्वेशन को हम मैग्नेट के केस में रिप्लेस कर सकते हैं कि at place of P, at place of electric dipole moment, we will take magnetic dipole moment. At place of electric field, we will take what is magnetic field. It means this formula is similar to the formula which already we have derived for the torque experienced by an electric dipole in a uniform electric field at an angle theta. This torque will be maximum when theta is equal to 90 degree. When theta 90, then torque becomes maximum, and when theta becomes 0 degree or 180 degree, then in that case the torque is released by this bar magnet in this magnetic field is equal to 0. So in this way we can find out under what condition the torque acting on this bar magnet is maximum or 0. Now next topic is current carrying solenoid we have as an equivalent to a bar magnet. We know that we will take a bar magnet. So in any bar magnet like this one, suppose one is what pole north pole and other is what pole south pole. A magnet is always possess the two poles north and south. Even if the magnet is break into atom, so that atom भी always also possess the north and south pole. ये मत सोचिएगा कि हम यहाँ से इसको तोड़ दें तो नॉर्थ अलग हो जाएगा साउथ अलग हो जाएगा, नहीं, जहां से ये टूटेगा, सपोज ये नॉर्थ यहां से आपने तोड़ दिया तो ये साउथ हो जाएगा, एंड फॉर दिस वन दिस साउथ दिस वन इज नॉर्थ. इट मींस व्हेन यू विल ब्रेक ए मैग्नेट or in any magnet the pole cannot be separated from each other. So in a case of a bar magnet there are always two poles, and you know like poles always repel while the unlike pole is attract. Like pole means like north repel, south repel, but north and south pole attract. And also when a bar magnet is suspended freely from its center of gravity in horizontal plane, then always it rests in north and south. It is a property of a bar magnet. But it also observed that a current carrying solenoid, we will take a current carrying solenoid, and that current carrying solenoid is also suspended, then it also comes in rest in north and south. और मैंने बताया नॉर्थ और साउथ में कौन रेस्ट करता था, बार मैग्नेट. And also it observed that the two current carrying solenoid is also shows either attraction or repulsion, which shows by the like or unlike poles of a bar magnet. So in this way we can say a current carrying solenoid is behaves are equivalent to a bar magnet. And also I hope maybe all of you know in the class 9 or 10 it was given here. Suppose this one is a current carrying solenoid or current carrying coil. This one is a current carrying coil, and suppose here current is clockwise and here the current is anti-clockwise. So on the basis of this clockwise or anti-clockwise current, so this one is a current loop, and also same concept will use for current carrying solenoid. So this one is a current loop, and this current carrying loop is behaves like a bar magnet or behaves like a magnet. अगर ये एक मैग्नेट की तरह बिहेव कर रहा है तो इसमें दो पोल होंगे, कौन कौन से, नॉर्थ और साउथ. तो आवर एम इज टू फाइंड, हमको कैसे पता चलेगा कौन नॉर्थ पोल है और कौन साउथ पोल. तो यू लुक फ्रॉम वन साइड, आप एक तरफ से देखिए. इफ द करंट इज लुकिंग क्लॉकवाइज, जिस तरफ से आपको करंट क्लॉकवाइज लग रहा है, इसका मतलब वो पोल कौन सा पोल है, नॉर्थ पोल. वो पोल क्या है, साउथ पोल. सर, if the current is looking clockwise, then that pole is behaves like a south pole, and behind it what pole, north pole. And if the current is looking anti-clockwise from any phase, आप किसी एक phase से देखिएगा, and if the current is looking anti-clockwise from that phase, it means that phase is act as a what pole, north pole, and behind it what pole here, south pole. So in this way you can find out the north and south pole in a current carrying solenoid or in a current carrying coil. Now next topic is magnetic line of forces. As you know, like electric line of forces in electrostatics, here I am going to discuss about the magnetic line of forces. And what is the magnetic line of forces? The magnetic line of forces are the line of forces in a magnetic field. हमने बताया था इलेक्ट्रिक लाइन ऑफ फोर्स इलेक्ट्रिक फील्ड में ड्रॉ किया जाएगा, और मैग्नेटिक लाइन ऑफ फोर्सेस विल ऑलवेज ड्रॉ इन मैग्नेटिक फील्ड. सो इन ए मैग्नेटिक फील्ड आर दोज इमेजिनरी लाइंस व्हिच कंटीन्यूअसली represent the direction of magnetic field and the tangent drawn on any point on the line of the force shows the direction of magnetic field at that point. It means simply you can say here a magnetic line of forces are those imaginary curve in a magnetic field which always represent the magnetic field. And if you want to find out the direction of the magnetic field at any point, so simply you will draw the tangent at that point, and the direction of the tangent will be what here, direction of the magnetic field at that point here. Direction of magnetic field at that point. So in this way we can define the magnetic line of forces and the properties of the magnetic line of forces. So I hope maybe all of you know the properties of the electric line of forces. Now you see what is the property of the magnetic line of forces. A magnetic line of forces will always start from north pole, form a loop or form a curve, comes to south pole, and again it come back from south pole to north pole. So in this way you can say a magnetic line of force will always form a closed path or closed loop, while electric line of forces always start from positive and end at negative, but it will be never form a closed path. So remember this, if anybody asks to you, what is the difference between the magnetic line of forces and electric line of forces? So magnetic line of forces will always form a closed path, while the electric line of forces will never form a closed path. Second thing here, two magnetic line of forces will never intersect to each other. While at the intersection point, you can draw the two tangent, and two tangent means two direction of magnetic field. And at one point, two direction of magnetic field is not possible. Due to this reason, two magnetic line of forces will never intersect to each other. In a magnet, near the pole, magnetic field is stronger, and where the magnetic field is stronger, at that point magnetic line of forces are very close to each other. And as we go away or far from the poles, then magnetic field strength decreases. And when magnetic field strength decreases, then at that point the magnetic line of forces is what here, far from each other. तो अगर कहीं पे मैग्नेटिक लाइन ऑफ फोर्सेस आपको दिखाएगा बहुत पास पास हो, इसका मतलब उस रीजन में मैग्नेटिक फील्ड स्ट्रेंथ स्ट्रॉन्ग है, और जहां पे मैग्नेटिक लाइन ऑफ फोर्सेस दूर दूर रहे वहां पे क्या है, मैग्नेटिक फील्ड स्ट्रेंथ कम है. एंड ए यूनिफॉर्म मैग्नेटिक फील्ड, मैग्नेटिक लाइन ऑफ फोर्सेस पर बढ़िए आप क्या लेते हैं वहां पे जहां पे एक जैसे पैरेलल टाइप करेंगे तो मैग्नेटिक लाइन ऑफ फोर्सेस. बट रिमेंबर दिस difference is what here between magnetic line of forces and electric line of forces. Magnetic line of forces form closed loop, closed path. Start from north, comes to south, and again come back from south to north. While electric line of forces start from positive and end at negative. वहीं खत्म होता है. So in this video, this topic or this chapter is completed here. Please today you go through this topic here, what I have discussed in this chapter, and next time we will start the next chapter.